Schahram and then pass it to him. So it's my great pleasure to introduce our third keynote speaker, Schahram Dustdar. Schahram is a full professor of computer science at Vienna University of Technology. Schahram also is the head of distributed systems group at Vienna University. Schahram holds a number of honorary positions. These include University of California, Los Angeles, Monash University, Melbourne, Australia. Oh, sorry, Schahram, you cannot hear me? Sorry, I'm stopping here. Schahram, can you hear me?
I can hear you fine, so maybe it's a problem with the audio settings.
Can you hear me, Harry?
Yes, I can hear you. Can you hear me?
Yes, everything is fine.
Fantastic. So if it's okay, I can continue. So that's fine. Thank you. So I was talking about your honorary positions at, again, I repeat, University of California, Monash University, Melbourne, Australia, Shanghai University, Macquarie University in Sydney, Australia, University of Groningen, the Netherlands, and also from December 2016 until January 2017, Schahram was a visiting professor at University of Sevilla, Spain, and from January until June 2017, he was a visiting professor at the Berkeley, USA. Schahram is an ACM distinguished scientist and a member of Academia Europaea, where he's chairman of the informatics section. He was named an IEEE Fellow in 2016 for his contributions to elastic computing for cloud applications. And he was also recipient of the IBM Faculty Award in 2012. He is the co-editor-in-chief of the ACM Transactions on Internet of Things, the editor-in-chief of Computing, Springer. He is an associated editor of IEEE Transactions in Services Computing, IEEE Transactions on Cloud Computing, ACM Transactions on the Web, and ACM Transactions on Internet Technology. And he's also on the editorial board of IEEE Internet Computing and IEEE Computer. According to Google Scholar, Schahram has over 34,000 citations. That's really impressive, with each index of 74. This is why Schahram is one of the most influential researchers in the field of internet technology, service-oriented architectures, and computing. His research also involves mobile and ubiquitous computing, context-aware computing, complex autonomic and adaptive systems, as well as data services and novel programming models for computational science and engineering. His current research involves edge, fog, and cloud computing, and today we are going to hear from him about the edge intelligence, understanding the convergence of edge, fog, and cloud. So without further ado, let's welcome our keynote speaker, Schahram Dustdar. So I pass it over to you, Schahram.
Thank you very much. So I try to share my screen. I hope that works. I just had massive problems this morning with, can you see my screen?
Yes, it's working. You can only put it in a full, yeah, fantastic.
That's good. All right, wonderful. Thank you very much, Barry, for your kind introduction. Yeah, I had problems, last minute problems with Zoom, and nothing was working. So
not only you.
Yeah, so I was trying to go switch to a different computer, etc. So it was a bit stressful. So anyway, so thanks for being here. So this talk is about edge intelligence, and I'm trying to put together the different topics of edge, fog, cloud, IoT, etc., and all the rest of it into a coherent framework, and to discuss with you what are the current challenges as I see them actually. To start off, I would like to say that I think that we are moving towards a time that we are having a big task at hand, and that is to create elastic systems. And what I mean with elastic systems, I will tell you in a minute. Those elastic systems are composed of three components, which are typically being woven together. And that is people, software services, and things. In the past, people were actually considered outside the system, interacting with the system, and not primarily a concern of typical distributed systems infrastructure type of activities. They were more kind of interfacing with the systems that were built. Software services and hardware services were typically of prime concern, that's true. And the things in the sense of Internet of Things, they were also outside the scope of all of the systems that we typically were concerned with as computer scientists, more a domain of electrical engineers, for example. But nowadays we have different types of applications such as smart homes, health networks, governmental networks, transportation networks, and even smart grid networks. All of these different types of systems increasingly actually require to different weights, with different weights to involve people as prime concerns, software services and things at the same time. And the general question that we as designers of these systems have to deal with is, how do we actually design, model, manage, monitor, govern such systems which have these three different building blocks, which is kind of a challenge in its own right. Now, we can see that all of these different building blocks are essentially connected. I would like to bring this example of these rubber bands, right? So we have these different nodes, and basically the system has to grow and shrink with different types of weights between the different nodes. And those nodes being people, software services, or things. And essentially where I would like to bring this analogy is to look at nature. If we look at nature, like in this picture, we can see that there is this marine ecosystem having the sun, the birds, the animals, the rocks, the water, and the plants in it being connected with each other. And this connection actually is represented by these yellow arrows. So there is this ecosystem that we can learn from. And we can learn from it because it's a complex system similar to the systems that we are trying to build. And it has intrinsic adaptive behavior. And this comes with 4 important properties that we actually try to mimic in our systems. The first one is that the system in itself is robust and resilient. And robustness means not that it is rigid, quite the contrary. It's actually in the sense of Nassim Taleb's anti-fragility. Resilience brings with it the way that exactly these rubber bands were showcasing, namely that you can achieve this stability even if there is some disruption simply by shifting the focus of this overall network. Secondly, there are always measures of health. So in other words, we always know what are the key indicators in such ecosystems. Where do things go wrong, and where is everything is in balance, is in harmony. Thirdly, we have a built-in coherence in such ecosystems. This means that essentially the system itself has a certain purpose that it tries to achieve, in a sense that everything remains in harmony. And fourth, connected to that, it always resists entropy to a certain degree, in a certain timeline. Meaning that if no big disruptions occur, the system remains entropy resistant. And this is basically what I try to mimic. And if we translate that into ecosystems for distributed systems, we can basically say that, okay, in the sense, in an analogy from nature, where we had, all these different actors, we also have these different actors like compute power, networking, storage, different devices, networks, etc., in the IT world. So what are then the principles for these ecosystems in the IT world, which we try to create these ecosystems for. A good example where we can look at this all together is a smart city. In a smart city, typically we have all the things in the sense of Internet of Things. We have these containers, the sensors for air, traffic, fire, water, etc. All these cameras in place. We have different software services, like they do intake the different data from the things. So they provide traffic control, disaster management, detection of people, facility management, and the like. We have us as the people running around in these cities with our Fitbits and the smartphones, etc. And we have all that data that is being created along the line. So these are typically the ecosystem players similar to what we see in nature, right? Now, what we have done in the last 10 years as a big computer science community, 10, 15 years or so, is basically to provide everything as a service. So this was, I think, the big success of the service-oriented architecture, that it actually had this notion of providing everything as a service as we moved along. And that actually also enabled cloud computing as a principle to become mainstream. Now we have everything as a service, but actually that doesn't completely help us to move on like we have in the cloud. So there is one key observation. There are some new families of application that are actually requiring some real-time location-based access to data from the environment at different levels of this fidelity and different levels of granularity as well. And we need appropriate compute and storage resources in close proximity to the data producers and consumers. This is something that is actually a little bit uncomfortable for typical cloud architectures. Because of these high latency requirements, we come to different types of interesting problems. One of these problems I would like to highlight in this chart, what I call dynamic analytics. What I mean here is that typically in the past, we have built our applications using vertical domains. We do have also horizontal domains of concern, like monitoring and control, etc. But most of the application, the systems that we built are verticals. So for example, we have the financial systems vertical, the banking vertical, the factory vertical, the education vertical, etc., etc. However, if you observe what is happening in the last couple of years, we are increasingly having the requirements to actually move to transcending these boundaries of typical vertical silos, something that actually service orientation was claiming to address, right? So some examples which we see every day now in our lives is basically if we want to analyze the well-being of a certain region, a cluster, and a street, and different types of entities, we encounter a problem of actually crossing the boundaries of different vertical systems. And this is increasingly becoming a problem because the systems that we have designed in the past, they had kind of rigid boundaries in place. And integrating all of these different systems at the later stage becomes a big hassle, even with the service orientation in place. So what is the solution? Well, the solution I propose is to actually rethink the divide and conquer principle, which is basically a principle which served us very well in the last 50 years, especially in computer science, but also in other engineering disciplines, which basically comes from military strategy. It says that as long as you divide, you can conquer different areas and you try to keep the enemies kind of fighting with each other. And I think that this analogy from military is actually only good up to a certain complexity of a system. So what do I mean? I mean that these systems that we have to build now constantly have to adapt to different prime concerns. And these prime concerns, for example, represent themselves in system boundaries, but also in quality of service attributes, for example. For example, focusing on structuring the topology of the system based on quality of service attributes, or on contextual properties, or on another dimension, also on the cost dimension, right? So you want to be able to structure or restructure the topology of your system and different aspects of your system based on different criteria. And in the best case, you would like to do that in real time. And actually, the very architecture of a computer itself is also quite rigid. And in the future, we might also be able to move towards different types of interfaces in the general architecture of a compute system. For example, rethinking the divide of the memory and the compute in a computer. And this paper, which just appeared a couple of days ago, basically talks and shows about different research in this space. And I think that this is kind of interesting to think about it, because this divide and conquer principle is so deeply rooted in all of us in computer science that it is, I think, time to rethink it. Not that I have a solution for this, but there are some indications where we might go. And I will discuss some of the ideas where we might go with this. So let us ground this a little bit into today's infrastructure principles. So there are different perspectives on distributed systems infrastructures. Basically, there are two as predominant ones. The first one is the cloud-centric perspective, as I call it. So the cloud is the center of the universe in this perspective. It looks at the cloud as the center and everything is around it. So all the data that is coming in, for example, from the sensors is being shifted and moved to the cloud. The magic sauce is in the cloud, and the decision-making, the model building, all the AI, everything that you can think of is kind of the brain. Everything happens there and is then pushed back to the boundaries of the network. That's what I call the cloud-centric perspective. The other perspective is the internet-centric perspective, which by nature basically says, no, the internet is the center of the internet and nothing else. And it's basically connecting all of these different players in such an ecosystem. And as you can imagine, these different perspectives have a number of assumptions and properties. Well, the cloud-centric perspectives assume that everything is stored on the cloud and everything else is just offloading to the cloud. The whole magic is on the cloud. Edge computers are just supporting. Everything else is just a supporting role. And this basically means that we have a centralized network architecture. And without the cloud data centers that are out there, nothing can actually be done. And actually, even this very morning, with having access to Zoom and being able to log in, shows exactly that perspective that we are now trapped in. The internet-centric perspective basically allows for some autonomy at the edges of the network. And I think that this is, of course, the direction that we should move towards. So we should be able to have some intelligence at the edges of the network as well, where the data are actually being processed, and decision-making could also be done at the edges of the network, where latency, etc., is lower as well. Now, if we put this picture together, we can say that we have a multi-tier type of situation here. On the left-hand side, you can see the end devices, the IoT sensors and low-powered edge devices, which have low reliability. They are highly volatile, they are mobile, they have energy constraints, etc. Some of them are owned by the user, some of them are owned by service providers, maybe more so in the future. And we move from those to edge devices or edge telecom operator controlled devices, possibly, to the fog, which is definitely telecom provider, base stations, for example, and then to the cloud, which is distributed maybe over a couple of cloud data centers, which has unlimited, under quotes, compute and storage capability. So the question for distributed systems then becomes, how can we actually spread the applications, the systems that we are developing over this whole IoT edge fog cloud continuum. And how is that distributed? Are we, as the designers of these systems, able to say this part should run here, this part should run over there, or is the infrastructure taking care of it? So if we break that even down to the key questions, we can say basically the key questions are vertical and horizontal distribution of everything that you can think of. It is not just offloading of compute and storage horizontally or vertically in these different tiers, but also thinking about what it actually means for software engineering. So how do we have to deal with designing these systems for all of these different players in this overall zoo, as I call it, because we have now a plenty different varieties of different devices in this new world, ranging from very computational, powerful base stations down to Raspberry Pis with very limited amount of compute and storage capability. So how do we actually navigate this whole new continuum of compute devices? As you can see here, there are many different compute devices, which many of us might be not dealing with on a day-to-day basis, from data centers to mini servers to micro clouds. But it's actually a very interesting set of questions. How do we actually deal with all of these specialized compute platforms now popping up? Because all of these AI-empowered specialty cards are being stacked on top of typical Raspberry Pis and other devices, bringing more intelligence towards the ends, the edges of the network. So is it possible, we might ask ourselves, to write once and run anywhere on this whole continuum of compute platforms, which is extremely broad, from really microcomputers to big kind of installments in the urban areas, in the cities, right? So what we are seeing are software intensive edge systems. And I think that we need to rethink how we actually support the design and operations in that environment. So the DevOps part of this becomes extremely prominent as well. And there are some fundamental conflicting factors that we have to think about explicitly. And this is one of my core arguments in this talk, that we need to bring this to the forefront. And the forefront has to deal with the question of latency, because there is a inherent traditional division of cloud IoT, and the latency awareness is becoming more and more important for different types of applications, such as augmented reality, virtual reality, autonomous driving, and all of that. So latency, as we have it in cloud-based systems, is simply not good enough for a new family of types of applications that we encounter today. So this is where edge computing has gained some prominence. And secondly, following this is basically the idea of security, privacy, and safety. And if you bring in these questions, of course, this is a set of very good arguments for the edge, provided that you actually deal with it as a first-class citizen, right? So if you have edge systems which deal with security and privacy, you have a very good chance to actually deal with privacy as a first-class citizen versus dealing with it on a higher level, namely on the cloud. And of course, locality and mobility with different administrative domains, introducing novel challenges with the question of evolution of the system and configuration of the software itself. So the question is, which characteristics of edge computing systems should be actually abstracted as first-class citizens into the underpinning model of what we are thinking of actually doing? So one hypothesis is, okay, proximity is important, context is important, capabilities are important, energy is important. But I would like to translate that, and in this presentation mainly deal with what I call here elastic diffusion. What is elastic diffusion? So let us decompose this extremely important property, as I think, for the distributed systems infrastructures that we are building and also the software that we are building. First, let's look at elasticity. My claim is that these yellow arrows that I was talking about in the beginning in the natural ecosystem, which are building this resilience mechanism there, are actually a very important property of this ecosystem. So elasticity is a property in physics and material science saying something about the state of following some deformation. So you have some material, you put stress on it, it deforms. If you take away that stress, it goes back to its initial form. Similar represented by these rubber bands on the hands I had in the beginning, right? And this is exactly what I would like to mimic in our systems. Now, cloud computing is, of course, saying that this is exactly what it is doing. However, my claim is that, in my opinion, in the context of cloud computing, we are mainly dealing with scalability, really, because we have it only on the domain of resource elasticity. So in my understanding, the cloud deals with elasticity in the cloud terms only with one dimension. And the semantics I would like to give to elasticity is that it's actually within a three-dimensional space like represented in this picture. So one dimension is the resource elasticity, but there are two other very important dimensions, as you can see here. One is the space of non-functional parameters. So all the quality attributes, quality of the data, the granularity of the data, the fidelity of the data. Those are important aspects. Thirdly, also the costs are very important nowadays. So my claim then here is that the designer of applications of systems should be able to always create the application within this three-dimensional trade-off model so that he or she is able to specify the application operating in this space of this elasticity. So every application has as kind of a signature inside this three-dimensional space. For example, you might want to say, okay, I always want to have fresh data from the IoT sensors, but not under all circumstances, right? So I'm ready to have fresh data, maximum fresh data, but only if it doesn't cost more than X amount of euro, right? So this little example shows that you actually are concerned with some quality attributes because you actually take that data as an input, do something with it, and can move it forward into the next stage of the workflow, but only if the quality of the data, for example, the resolution of the data, is fulfilling a certain quality. Otherwise, you would not be able to move it forward to the next stage of the workflow. So in other words, what you would like to ensure is that the quality attributes are also met. And these quality attributes can be a lot of these things, right? Combined with the cost, of course. So what we have done basically then is in a project a number of years back, we have implemented this elasticity control in a language and mapped that onto a cloud infrastructure where we are able to attach elasticity requirements, as I was just highlighting, to different abstractions, to cloud service level, to services, even to code regions. If I have a code that I have written but not actually is belonging to myself, I can attach these elasticity attributes to that code. And the project Cellar in those years was actually able then to shift the deployment of these different services, implementing those functions on different virtual machines in the cloud in order to fulfill these requirements that I have specified in there. And the representation on the right-hand side shows that whenever a criteria on the left-hand side is not met, it's represented with a red dot, and automatically, or with the help of an administrator, can be shifted to a different virtual machine. So that was a project a number of years ago. And now we are shifting this and bringing this philosophy, if you like, this mechanism of elasticity to the overall continuum of the compute infrastructure from IoT, edge, fog, and cloud, because it needs to be spread. So the elasticity principle is not only for the cloud, it's actually along the whole value chain of the applications. So that at any point in time, if you look at an application in this three-dimensional space represented by this triangle of resource, quality, and cost, you can say something about this space function. Is my application actually inside these boundaries I have specified, or am I losing money? And in particular, up to a certain view that you're interested in, is it moving along the pathway that I have specified as well? So with these two functions, you are pretty much able to say a lot about your application, how it is behaving inside your elasticity specification. And that is pretty exciting. So that's all very nice. And now we have to move it to this whole continuum of this edge, fog, and cloud part. The second aspect of it is the diffusion part. So for this diffusion part, we have named this osmotic computing. Osmosis is a principle from chemistry. So first we stole this principle from physics. Now we are stealing something from chemistry. So we are obsessed with nature, as you can see. In chemistry, the principle of osmosis represents the seamless diffusion of molecules from a higher to a lower concentration solution, right? Represented by this figure here. And this principle is, I think, very useful for us in the computer science domain to think of it as a push and pull mechanism, right? So this push and pull mechanism needs to be implemented in the infrastructure. And that is the fundamental claim that I'm doing here, namely that the microservices, for example, that have to be deployed across cloud and edge infrastructures need to have the intelligence embedded in the infrastructure to know where they need to be running on. Should they run on cloud data centers? And if so, where? Or should they be moving to the edge, right? So you can look at this whole continuum and see then services being shifted along this whole continuum of cloud and fog and edge. And under the name of osmotic computing, we are a bunch of labs across Europe, maybe also worldwide. We have started this movement under the term osmotic.org. And we are happy to welcome you there. We are just a number of university groups, putting together our prototypes, trying to put our papers and software prototypes open source in order to make some progress in this space. So if you're interested to contribute, please do send me an email. So these two principles of elasticity and osmosis are conceptually, I don't go into the details here because this is just a keynote talk, are the main principles in order to organize something that we call a distributed systems infrastructure of the future. Now, how do we bring in intelligence? So as I was saying before, this whole topology of this infrastructure, this computational fabric, in a sense, needs to be intelligent. Intelligent in a sense that we cannot do that manually. It needs to be automated, obviously, right? And this level of automation has to reach a certain degree, which is beyond what we have seen before. So it needs to allow for training, for monitoring, and creating these models, changing these models, etc. And it makes it extremely difficult to do because we have heterogeneous applications and different models, and this requires a flexible but also modular infrastructure and it also needs intelligent operations. And it needs to be be automated along the AI application lifecycle down to the edge. So it's not sufficient to do all of this magic just in the cloud as we see it today. We need to be able to move all of this also to the edge. So the edge needs to become a player in this as well. So what is the fabric for this edge intelligence? First of all, it is sensing. So a large number of dynamic and mobile publish and subscribers of this data have to become members of this edge intelligence. So we need to go beyond this traditional messaging services that we see in Amazon Web Service IoT or Microsoft IoT Hub. So this management and the governance of this whole thing needs to become distributed and also decentralized. Secondly, edge computers and computer networks with modular AI capabilities are now becoming part of this ecosystem. As you have seen in the beginning, a lot of these AI cards are being attached to the compute and even to very simple IoT devices like cameras, so that those cameras are not just cameras feeding data streams into the cloud, but actually can do some AI calculations on them as well. And this is very important. And thirdly, of course, you need to have an intelligent orchestration and coordination of this overall infrastructure. So how do you actually do that? Because in the past, you were pretty much bound to a centralized orchestrating mechanism. And now we have to do that all decentralized and distributed. And that's a big research challenge, which will, I think, take us many years to actually make good progress for that. We have experimented in this space, in the fabric of this, with our little Raspberry Pi clusters that we have created, put on top with some AI cards, in which we experiment with energy awareness and shifting workloads between these different Raspberry Pis, just to make our point that this is actually possible. This diffusion aspect and distribution aspect is actually possible. So if you're interested in following what we do, here are some pointers to that. Now, if we look into the question of, okay, how do we actually do this learning, this federated learning in distributed systems? It is quite astounding that, of course, these communities in the past have been pretty separated, right? So we have federated learning on one hand side, the AI community, and of course we have this systems and distributed systems communities. But now we have to bring those together because we have to train the data, training on that data directly on these remote devices and not send everything to the cloud. We have to do that without revealing the data themselves. We have to send outcome of local training to maybe servers. And the question is actually just, what data do we send? How can we train the data? How do we create these models? And how do we make these models available to these devices? So there are plenty of questions that we have to try to answer here. And the applications are immense. We have applications for mobile devices such as next word prediction, face detection, and voice recognition, which we are kind of aware of today, but also for organizations such as hospitals, for example. You would like to share data with other hospitals or medical professionals, but not expose the data of the patient themselves. But also for environmental, transportation, smart homes, and many other applications, you can find use cases for this. So increasingly, it is becoming important to shift this learning infrastructure into the systems infrastructure. More research challenges at hand, like device recruitment strategies. So which subset of the devices do you assign to this learning task, right? You have to take into account the processing, the storage, the battery, the trustworthiness of the device, the quality of the data that it provides, and other criteria. The volatility, the devices can appear or disappear at any time. What do you do when the device does not submit the data in a timely manner, right? Inaccuracies, if you have non-independent and identically distributed data. Heterogeneity in the volume of the training data per device. So if one device contributes a lot of this training data, that might actually lead to a biased model. How do you counter that? Preventing privacy leaks. So some private information may be inferred even if the devices do not transmit the actual data as we know it. And also incentives to misbehave. So if I own this edge device, why should I waste battery if I can let others do the work? So these are just some examples of research challenges along this food chain of the intelligence fabric. Now, when we looked at this, we thought, okay, let's create a research roadmap thinking about the quality of the experience of the human, and actually bring this down into the question of AI on the edge and AI for the edge. But let's start at the top. So the quality of the experience basically for the human side is fivefold. The first one is, of course, the performance. I feel the performance I have is related to the ratio of computational offloading along the line of this whole topology. Secondly, the cost. Computation, communication, energy consumption, these are all cost aspects that play into this. Privacy and security, as I said, okay, federated learning, aggregating these local machine models from these distributed edge devices is of concern here. Efficiency, so how can I have excellent performance with a very low overhead? Do I do model compression, conditional computation, and the like? And finally, reliability. So this relates to the model upload and download and wireless network congestions. So these are the 5 prime concerns from the quality of experience level, so that we as humans actually experience from this edge intelligence infrastructure. Now, if we decompose that into what role does actually AI play, we can see that there are 2 basic fundamental building blocks. One is, as we call it here, AI for the edge, dealing with the topology of the edge orchestration coordination with these base stations, as I was calling it, with the content. So do we have lightweight service frameworks for all of these quality of service aware services, for example, on these mobile devices? And thirdly, services. So computation, offloading, user profile migration, and the management of the mobility. So these are concerns where AI for the edge helps. There are also grand challenges here. How do I establish the model, optimize the model, and restrain the optimization model? How do I develop the algorithms there? And how do I create this trade-off between the optimality and the efficiency of these models, especially considering that we are dealing with constraints on these smaller devices on the edge? The AI on the edge has also its own challenges regarding data availability, so that there is this challenge that we might have a lack of availability and usability of this raw training data. And if we don't have that data, it leads directly into a bias. How do we actually counter that? Secondly, how do we select the models? So the state of the art actually requires the selection of these need to be trained AI models. And that has challenges in our world here, right? How do we come to the thresholds of this learning accuracy and the scale of these AI models for the quick deployment and delivery that we need in this infrastructure? And how do we select and probe training frameworks and accelerator architectures under these limited resources? And thirdly, the coordination mechanisms between these different edge devices, the cloud, and all these middlewares and APIs that come in between of all of this. So managing the whole AI lifecycle, as I was highlighting here, is a very difficult aspect. And in the past, or actually even today, all of this is basically centralized and done on the cloud. At least the data is sent to the cloud. Now we have to think about how can we distribute that. And we have created a research here in this paper where we look into this AI operations workflows, looking at it from, as you can see on the left-hand side, cloud to cloud or cloud to edge, edge to cloud, and edge to edge concerns. And we discuss those regarding the data characteristics, the model characteristics, which enabling technologies are out there, and some example use cases that you can see here. I don't have the time because I also want to get to the Q&A part to go into more details. But here you have a summary of these because the concerns are plenty if you look at this whole topology that we are dealing with. To summarize, basically what we have learned here is that nowadays we are dealing with the whole compute continuum, which is ranging from IoT, edge, fog, and cloud. And that continuum is becoming bigger, not smaller. Secondly, we are dealing with an ecosystem of this whole infrastructure, basically, right? And we have to look into these automation, higher levels of automation, and differentiate between AI for the edge and AI on the edge, which bring with them a lot of research challenges. And we have to have a clear understanding of this edge intelligence AI fabric and understanding that this is an ecosystem and we need to transcend these usual boundaries that we are seeing nowadays. So my claim here is that we need to move, make a significant step forward because this, the way that we are creating these infrastructures is simply not good enough for the future. And possibly also we end up with novel architectures for the computers themselves if we look at this whole continuum. And with that, I want to thank you very much for your attention, and I'm happy to go into the Q&A. Ari. Thank you very much.
Thank you, Schahram. Thank you. That was a great talk, very interesting and informative. So look, we could ask to send your question in the chat, but I like to hear your voice. So sure. Anyone wants to go ahead?
This is Frank. Maybe I have a question. Hi, Schahram.
Hello.
I do have a question which is not AI specific, as a distributed systems question. So do we need to give up the write once and run everywhere principle and go back to hardware software co-design with the advent of all the different devices, which would be a shock to me?
Yeah, so I was talking to, in this paper, Rethinking Divide and Conquer, actually, I had this work done with one of the leading computer architects, at least in the academic world. And it looks to me that, yes, we might consider that that what we are doing in the world of software, that we constantly need to redesign and have this automation in changing the, based on quality of service, etc., the topology. This actually might also be the case for hardware-software co-design. Okay. So in other words, he showed me, and I read, there are many papers actually out there, which is basically showing that increasingly the interfaces, the standardized interfaces that we have in the architecture of computers and the separation of compute, data, memory, etc., that we have today, comes with a huge loss in performance as well. So it might well be that we have in the future novel computers which are actually spread and completely different than what we see today, and having different interfaces as today. So a keyword would be moving kind of data to the memory and do the computation in the memory versus other ways of distributing all of this. So I think that it's quite likely and possible that these things actually change in the future. I don't think that the architectures that we have since, I don't know, 50, 60 years or even longer are remaining forever.
Okay, thank you.
Thank you. Any other question? Next question, anyone? Please.
Hello.
Yes, who is this?
Here, Doug. It's Doug. Hello.
Oh, Dirk. Hi, how are you? Nice to see you, ECU.
Nice to see you again.
Please go ahead.
Hello, Pari. Yeah, hello, Schahram. Thanks a lot. Yeah, two questions actually. First one, this proximity question, how urgent is it to have such edge computing paradigm actually? So we see that definitely, but on the other hand, we still have the dark fiber with unused capacities, right? So sometimes, same discussion as with content delivery networks, we sometimes hear from some experts that this is rather due to the greediness of the internet service providers, but not due to the physical capabilities, right, of what we could do. So is there some intrinsic need? I don't have a good feeling for that. That is a problem.
Yeah. Well, you know how it is, right? So it's not either or. Usually, it's all of the above, right? So I think that there are good indications that there are a number of families of applications and use cases which are coming into play, and this was my main argument, that especially these novel types of analytics that we have to do increasingly becomes impossible, and actually steering also the affairs of cities and societies is becoming more difficult without these principles. And I think that this is a very good, so it's not about having this one killer application and this is why we need to do everything fresh. I think it's becoming a fundamental issue for managing the society, I think. Because if you look at the current COVID situation, for example, it's from many of our professional perspectives. If you look at the whole logistics and things, how they are being done, it's bordering being ridiculous in some cases, right? So you're wondering what is actually happening there. You can see that systems, if they would be integrated much better, if we had better integration of sensor data, simulation, and actual data, we could be making much more progress that we would do as we are using the systems now.
Dirk,
I understand. Yeah.
Thank you.
Next question, Amy.
Yeah, I have a question. Can I?
Antonio?
Okay.
Yes,
hello.
Please.
Yeah, thank you very much. I really appreciate your presentation. I have a strong interest in missing data in IoT, and so the doing data imputation at the edge. So to this extent, do you have any advice, or maybe you have looked at this particular problem already, and any recommendations as to how you can use AI at the very edge to data imputation?
To reputation?
Imputation. So when you have missing data in IoT, is quite common to have missing data, and so you mentioned this quite cleverly.
Yes.
If you have missing data in the cloud, then you.
Yeah. No, we have not done personally that information that part yet. That's not our so far, because there are so many things that we need to do before. But if you're working in this space, I would be interested to learn. Maybe you can connect with me later on, and we can.
Okay. Yeah, sure. I'll send you a message of like. Okay. But thank you very much for your lecture.
Thank you.
Thank you. Next, anyone has any question?
Yes. Hello. May I have a question?
Yeah, one more. Yeah, we have time for one more question. Yes, please.
Yep. Thank you for your very impressive talk. I have a very simple, probably basic question. I heard recently there's a new called dual computing within the edge. I'm not sure. Did you involve any research in this aspect? What's the differences between dual computing, fog computing, edge computing? Which?
So this is dual computing, right? DEW. Is that what you mean?
Yes. I heard this. Yeah. Probably a little bit of explanation. Yeah. Okay.
Oh, I got it. Yeah. So basically, I think from a technology point of view, You can call it edge or fork. It doesn't really matter because this is a whole continuum. And as being a continuum, it is not necessarily only discrete steps, right? So I think the point that you have to look in, and this will change over the years, is what is the capacity of this device? So, let's say 10 years ago, the smartphones of today would be a super powerful computer, and now they're just a mobile device, right? And this will happen in the future as well. So what we call edge device and fork is there is a kind of a continuum. But when I speak of fork, it is more, I just give you an image so that you can relate to this more, is a kind of a base station operated by a telco provider. This is my perspective of a fork, because this fork is actually responsible for a multitude of different stations in a big cellular network, for example. So it is a bigger area of concern. An edge device, in my terminology, would be something much closer to where the data is being created. So something like either a mobile device, a Raspberry Pi, but also could be a server in a building, which is representing the whole computation offloading mechanisms that has to be done in one particular building. So you see the whole, let's say, differentiation is quite open. I think, and in the future, we might see some changes here as well, because let's say the telcos, if they step up to this game, they might become edge or fork providers of services. But maybe that doesn't happen. Maybe the IT companies acquire the telcos and then do the whole rest of it, and the things change again. I think this is just a differentiation to understand the computational power, the battery consumption, etc., the mobility aspects of these different devices along the food chain of these compute devices.
Thank you. I'm just conscious of time. You might have more questions. Look, if you have, you can send it in the chat. We're going to stay online because I need to announce the paper awards. I hope Schahram could stay as well. So Schahram, thank you so much for the great talk and also answering the questions. So if it's so okay, if you please, Schahram, yeah. Great. So now I can share the screen. Okay, so before I announce MOM's Best Paper Awards, yesterday we announced the iiWAS Best Paper Awards, and today we're doing it for MOM. But before that, I want to thank all our authors, because I want to congratulate all of them. Each paper, each really accepted paper makes a unique and important contribution to their own research area. But we had to rank these papers and select the top 2. And so we have 2 awards giving today. So the first one goes to with the title of A Dynamic Deep Trust Prediction Approach for Online Social Networks. This paper makes a great contribution to dynamic trust prediction, pairwise trust relations particularly, and considers the emotional state factor in trust prediction, something very novel. The first author, Mohsen Ghaffari, I think he's somewhere now among the participants. He just graduated this year from his PhD study. And the other co-authors are Amin Beheshti, Adita Joshi, Cecile Paris, Shahbar Yakhchi, Ali Reza Jolfai, Mehmed Orgun from Macquarie University and CSIRO Data 61, Australia. So congratulations to all of them, all the best. So I announced the second Best Paper Award, which is actually a Best Student Paper Award. with the title of Functional Gaze Prediction in Egocentric Video. I don't know if we have the first author here, but the first author, C. Ahmed Nas, is a PhD student. The other co-authors are Xiaolin Jiang, Stefan Seig, Yusheng Ji from Aalto University, Finland, and Japan's National Institute of Informatics. This paper makes an important contribution to gaze prediction in dynamic scenes, and their solution helps reducing the processing time on mobile displays. So congratulations to all these authors, well done. And now that I have your attention, look, today we continue. We have a very short break now. And after that, our sessions will start. As I said, we have 6 sessions happening, 3 in parallel, 2 for iiWAS, 1 for MOM. And another important talk happening today, our president of ACM, Gabby, is gonna talk and you can ask your questions. So make sure you attend. And I guess that's it. That's all from me. Thank you, everyone. See you around. Oh, just for the other sessions, every session has a specific Zoom link. Please go to the conference website, and if you click on the program PDF, you can find the Zoom link for each session. See you later during those sessions. Bye, everyone.
Thank you. Bye.
Congratulations, Mohsen. Okay.
Thank you so much. Appreciate it.
Bye, bye. See you later.
See you.
Bye.